Yeah, great. Thanks a lot for the invitation. Thanks everybody for coming. So yeah, I'm going to present a series of results related to Federated Byzantine Agreement that have appeared in multiple papers. And so this distribution is there from all these people you see here. And so I'm going to start by introducing the Federated Byzantine Agreement Model by building it up from classical quorum systems. Okay, and before I start, please interrupt me whenever you want if you have questions. I'm really happy to get questions. Okay, so it doesn't work anymore. Okay, so let's start with a really simple example. So we have a set of 4 servers, asynchronous network, meaning we have no bounds on how long messages take to be delivered. And we know that one server out of the 4 might fail, but we don't know which one. And we want to store a file here, a cat picture, obviously, reliably in the system for somebody to later come and retrieve it. Okay, and so a very simple protocol that works here is store the file, just make sure at least 3 servers get it, and to retrieve the file, just query any 3 of the servers, and whoever shows you a file that's correctly signed by the person who stored it, you use that file as my file. And so there are several things going on here. Because we have network asynchrony and false, we can never be sure that the 2 clients will access the same 3 servers. Because when this client here stores the image, so it receives acknowledgements from N2 to N4, and it cannot wait for N1 because for all it knows, N1 might be the false one. It has to go ahead with the 3, and same for now. In this case, things works out correctly because no matter how adversarial the network is, where the adversary is itself, any set of 3 will always overlap in at least 2, and so we'll have one server who has the image, assuming the retrieve comes after this one. Right? So very simple setting, I assume. And so the generalization of this is the theory of quorum system. So in the quorum system, we have a set of nodes, capital N. We have a set of quorums, which are subsets of the nodes. Those are the sets that nodes will access. So in our previous example, it was like 3 out of 4 sets. And then separately, we had a set of survivor sets, survivor system. Also, this is a set of subsets nodes, and those encode our assumptions about failures. So here, instead of assuming that at most one may fail, I'm assuming at least 3 survive. So this is called survivor set systems, and for those who know about fail-prone systems, fail-prone sets are dual. It's exactly the same. Okay, and then we'll say that a quorum system Q is quorum system for S, meaning it's compatible with the failure assumption if we have 2 things. So for liveness, we need that every survivor set contains a quorum, because we need to be able to access at least 1 quorum to store a picture. Right, and since we know that the set of correct processes is going to be a survivor set, if this is good. And then for safety, we need that every 2 quorums and 1 survivor set have one empty intersection. So we can see this easily in this picture. Right, so we are abstracting things a bit here. Q is the quorum accessed by client N. Q prime is the one accessed by client N prime. W is the real survivor set. Remember, we don't know which survivor set is the right one. So everything that's in blue here is well behaved, but everything outside it is malicious. So all of this is malicious, and so we need to have the intersection of these 3 sets to be non-empty. Okay, and then we can ask a question. Well, in what cases, if we make some particular failure assumptions, can we find the quorum system that will work?
In the first slide, the survivor sets were 2 of them?
In the first slide, the survivor sets were any set of 3.
Oh, any set.
Yeah, and because I started from the point of view of at most 1 might fail. Okay, so we have survivor sets and their dual fail-prone sets, but in this talk, we'll use survivor sets to solve the rest of it. That makes sense. Okay, so given some assumptions in terms of survivor sets, we can ask, is it possible to find a quorum system of assumptions? It's pretty easy to answer the question. It's going to be possible if any three survivor sets have non-empty intersection. Why? Because we said we want every survivor set to contain a quorum, so there might be a quorum inside this, a quorum inside that. This might be the true survivor set. So we better have a non-empty intersection. Otherwise, we'll have two quorums that do not contain, whose intersection do not contain any well-being terms. Okay, so far? Okay, and so for example, if this is violated, for example, if we have three servers and one failure, then the survivor sets are minus 2. Obviously, we have this example where the intersection is empty. Okay, so in summary, this is classic quorum systems and survivor sets. Questions about this? All right, so this formalism is basically the framework behind the classical distributed computing toolbox that was developed in the 80s and earlier, right? Once you make failure assumptions in terms of survivor set and you pick a quorum system that satisfies conditions, then you have a whole series of algorithms you can use for reliable broadcast, shared memory, emulation, group membership, atomic to make, you name it. So that's great, but the issue is that that was all developed for a centralized system where there is a system administrator that says, here are the quorums. Now, probably in this room, we care more about permissionless systems. So the question I'm going to ask is, can this framework work in a permissionless system? And it's pretty easy to see that, at least at first sight, it's going to be problematic because in a permissionless system, here I'm going to define it as a system where anybody can join or leave at any time without asking permission. So we don't know exactly who is in the system. Nobody knows. We have all kinds of issues. The attackers can create Sybil attacks in which they create puppets and join the system and they try to prolong the system. So a fixed set of quorums apparently will not work. So people came up with the idea of proof of stake to actually, in fact, kind of make it work with a few caveats, right? So here, I mean, I'm not going to spend time on this, but the very basic idea is to count money instead of identities, right? So we'll say that our survivor sets or any sets that together hold more than 2/3 of the money in the system, for example. And I mean, that's a fine solution, but it has a few caveats like long-range attacks. We all know about this. They're kind of hard to deal with. Maybe there's centralization risk because somebody might be very rich and now they control the system. Maybe some people might object to the fact that power to the richest. Okay, so alternatively, we could ask, why do we not let everybody who join the system make its own failure assumptions and make its own quorum system for themselves? Okay. So let's examine how that would work. Every node picks its own survivor set, double S subscript n. Yeah? This encodes the assumption of the node, and two nodes might have totally different survivor set systems. Same for the quorum system. We have now double Q subscript n. That's different for every different n potential. And so if we think about it a little bit, the requirement for the store retrieve protocol that we saw at the beginning to work will be a little bit similar. For liveness, it's pretty much the same thing, except that now we need every survivor set of node n to contain a quorum of node n. And then for safety, it's a little bit more complex. So we need the intersection of quorum of n, the quorum of n prime, and the union of the survivor set of n and the survivor set of n prime to be non-empty. That's probably a little complex to understand at first sight, but it's easy to see on the picture. So this is like before. We have a store retrieve protocol. The node n accesses Qn. This time it's quorum of node n. It's not quorum in general. Node n prime accesses a different quorum of node n prime. Okay. And now when will this work if we assume that the assumptions of good n and prime are satisfied? Or if we assume that the assumptions are satisfied, we know we have a survivor set of n. That's the real survivor set. We have a survivor set of n prime. That's the real survivor set. So we know that the blue area here is all well-behaved nodes. And so again, now we have the intersection of three things to be empty.
Go back one slide.
So I was describing this formula at the bottom.
So as survivor set Sn and survivor set Sn prime.
Totally, yeah. So it's purely already. And this survivor set is not recognized as a survivor set by n.
But still, everyone on the survivor set are correct.
Yeah, because here we're assuming we're dealing with two nodes n and prime that have made correct assumptions. So that the protocol will work if both make correct assumption and they satisfy this formula above.
Just to be clear, my assumptions are deciding both the quorum set system and the survivor set system. I have to make two decisions. Or
Yeah, in general, that's the idea. Yeah. Yeah, David?
And so, just to be clear, only one of them is the correct assumption, but
They both need to. I'm starting. My starting point is that they both make correct assumptions, and then I'm asking under what conditions will this allow them to stay in agreement, or to.
why do they both take the agreement of their survivor set?
No, so I'm assuming initially that they both make good assumptions.
All of it,
Yeah. Well, since I'm assuming that they both make correct assumptions, I don't get that the union of those two survival sets is actually correct.
Right, but obviously either one of them is correct.
Yes, but in this case, I need to change my formula. I don't know what it means to run a protocol between two nodes, and one of them doesn't even make correct assumptions. So I'm starting from the point of view that I want to guarantee something only for those who make correct assumptions.
Yeah, I mean, it could be, I don't know if you're making correct assumptions or not, but I never want to disagree with you. So like that could be like a valid.
Right.
It's like you're a student issue, like no matter what I want to do, you make crazy assumptions, then I just do the fix them later, and I just want to make sure I never disagree with you.
Right, but if I choose a survivor set that in fact is completely Byzantine delicious, then there's no way you can agree with me.
Sure, I can. If I prioritize.
Yeah. I mean, if it's totally Byzantine, yeah, I guess as long as I have an intersection here that's empty, then
Like my survivor set is correct. Yours is incorrect, but you're in all my corners. Like I should still be guaranteed never to disagree.
That's the way to do it. Yeah.
Yeah.
If the node itself is actually in all the forms, that works. Okay.
Actually, I have a basic, so I understand all this. It's a basic question. So it sounds like you are in your file retrieval example. It sounds like you're not assuming there's any erasure coding.
No, this is very simple. Just send the file.
Once you introduce erasure coding, the condition becomes a lot more complicated. You would need cardinality. Not just non-infinite.
Yeah, that would be a harder problem for sure. Yeah, I'm not considering.
Yeah. So you're just ignoring.
Yeah.
Okay. Fine.
Okay, and then same as before, if we take a set of survivor sets for each node, we can ask under what condition can I find a quorum system that works, and it's the same reason for just replace the quorums by survivor sets formula. And I'm guaranteed that I'll can find quorums that work. Okay, and then the good thing is that if you take this setup, so you might be thinking, okay, in a permissionless system, like why would those conditions hold, right? So random nodes come in that you make random assumptions, but maybe we can guarantee something if subset of system makes good assumption and satisfies, but maybe not because they might be tainted by the rest of the system. It's not clear that that should work, but in fact it does work. So if we take the following view, we say we have three types of nodes. We have faulty nodes, we have naive nodes, we have that are well behaved but they make wrong assumptions, and then we have wise nodes that are well behaved and make right assumptions. And we call a set G a guild when it's all wise and it satisfies its own assumption, meaning it has a survivor set inside it for all its members. So if we have this, we can solve reliable broadcasts. For example, we can share memory emulation. And this is basically with very nicely formalized this paper called asymmetric distributive trust. Okay, so maybe we don't need the proof of stake after all. We have a solution here. We just ask everybody to make their own assumptions, and here we go. Okay, so that will work for a subset of the system, but still, we would like to make this subset as big as possible. So maybe what we could say is, okay, we assume that we have a system where validators, nodes have public identities. We know who is running what validator, and we're going to assume that there's a kind of cartel that everybody more or less agrees on, and they're all going to put those nodes in their quorums of 5%, and things are going to work out. That's one assumption we make. And this, I think, is essentially what Ripple successfully supported. But the whole point with FBA is that we can do better than that. So how do we improve the situation? Okay, so the idea is that we're going to change the way we make assumptions. So instead of making assumptions only about failures, we're also going to make assumptions about others' assumptions. So I think you put it very nicely earlier. If I'm paraphrasing, I think you're not only going to assume that your friends are well behaved, but also that they're smart. Okay, so instead of calling the assumptions survivor sets, now we call them quorum slices. No need double S now. So we have each node pick a set of quorum slices. And the underlying assumptions is that the node has at least one quorum slice which is fully well behaved. And also, not only are they fully well behaved, but in turn, they make good assumptions. Now, if we unfold this definition recursively until we reach a fixed point, we'll get that we obtain minimal survivor sets where Q is supposed to W is W here. Also, so W is a minimal survivor set of N when N is in W, and also every member of W has a slice in W. Okay, so it will satisfy the recursive expansion of this definition. And to simplify, at this point, we're going to assume that survivor sets of quorums are equal. So this is also our definition of quorum. Okay. Any question about this definition?
Can you just go back to the definition? What needs to be a quorum? What needs to be a survivor set? What is the difference and what are we talking about?
So traditionally, the survivor sets are the assumptions about failures, and the quorums are what nodes actually try to access. And in some cases, let's say you have very big survivor sets that have a lot of overlap, then you can get away with choosing quorums that are smaller than your survivor sets. But what you can always do is say, okay, my quorums are going to be equal to the same as my survivor sets. That will work. Make sense? Yeah. But you can always make, you can always identify them and that will work. Okay. So let's try to take a few simple examples. So here we have nodes organized in a ring, and each node has a unique singleton slice, which is the next node in the ring. Okay. So can anybody tell me what the quorums are going to be in this situation? Maybe you're not allowed
I
to.
can.
Yes.
So one quorum is like that includes everyone, because every member of the quorum is in this set. Also, like everyone has a slice in this set as well.
Yeah, correct.
One possible.
So you're saying one possible quorum is just a set of all nodes. Yeah. And is there going to be another one?
That the survivor.
Also, yeah.
Oh, but that's also everyone's quorum.
Yeah, so in that model, we're going to now pick quorums that are just equal to our survivor sets. So survivor set and quorum is the same thing now from now on. Yeah, so that's
Are you assuming that a quorum with the empty set of quorum here?
so we still have this condition that we established before in an asymmetric quorum system. We want the intersection of every three survivor sets.
Okay, right.
Yeah.
Right.
Okay, so here there's only one quorum, one survivor set, all the nodes.
So it's always one. Always a quorum.
That's true, yeah, but in this case, it's the only one.
What about this sector?
Yeah, so if you take only yourself, you apply the definition. So let's say you're N1. You don't have a slice inside singleton N1. Your slice is you have to include N2. Wait, definition is here. And this is W instead of Q.
I see. No, I understand.
So I guess the dual to your picture on the next slide is everybody has the full set, but then as a slice, and then the quorum is every single.
Here, singletons are not quorums.
Everybody has a slice which contains everyone. If everybody has a slice that contains everyone, then every singleton is that.
No, because so for a quorum needs to have a slice of every one of its members inside it.
Like this set and one.
Yeah.
For example, every participant only has a single quorum, which includes everyone.
That's right. Yeah. Maybe it'll be clear on the second example. So let's say we have a system like this. Now I'm just going to use fractions here to denote the fact that here n has slices that consist of any two out of those three. So n has any two out of A, B, C as a slice. For this here, like B has any two out of 1, 2, 3, 4. So how do we build quorums here? Let's say we want to build a quorum of n. Well, we have to take one slice of n. Here it is. And now we have to take one slice for each of those included. This one, we take this one. And now we have a quorum.
They have to include each other themselves, so this is already satisfied.
Yeah, so those guys need 3 out of 4, but it's already satisfied. This is the quorum.
Not a minute. Remove it.
No, you cannot remove N3 because those ones need 3 out of 4 out of this. Okay, and we could also go like this. Is this the quorum? No, because N2 or N1 need 3 of those. So we do like this. Okay. Cool. So one thing to note is that there's going to be exponentially many quorums. So it might be a problem later. And the cool thing about it is that now we can take a system where we have two nodes here, n and prime. They've never heard of each other, and their slices are completely disjoint. Right? N has 2 out of 3 of ABC, and prime has 2 out of 3 of A prime, B prime, and C prime. And yet all their quorums will intersect. So with FBA, we were building asymmetric quorums, but not any kind. And we have this transitivity property that we can use to achieve sufficient quorum intersection. In fact, there's something maybe coined called the internet hypothesis, So this hypothesis says that if we were to deploy such an FBA, Federated Byzantine Agreement system globally, then like the current internet, market forces and so on will make it such that by transitivity, every node will be strongly connected to another node, and we'll have enough intersection quorums. If the hypothesis is true, then we solve the problem that we noted earlier with the asymmetric model, where hardly any reason that all quorums. Yeah, questions?
Would you say that this is basically formalizing what Ripple was plus? So like somehow everyone is connected to this cartel of nodes that everyone trusts.
In Ripple, I think they're assuming that everybody is directly connected in one hub to this cartel. Whereas here we can be connected to the cartel, but in multiple hubs. Like on the internet, not everybody is connected in one hub to everybody else. But the system as a whole is.
I guess the philosophical question this is that on the internet there's a little bit of somewhat similar resilience because IP addresses are allocated in a somewhat reasonable manner. But here anybody can kind of create as many events as they like it. Public keys.
Yeah.
So why do you think they are alike?
Yeah, that's a great question. I should have had a slide about this. But so if you consider the system, for example, if you add a new node somewhere, or 1,000 of them, single attack, and nobody trusts them, they have no effect at all on the core of the existing quorums. Yeah, I mean,
Maybe you want to say like any good paragraph will be someone takes those best purpose like for.
yeah. So the idea is that you'll know who runs which validator on the network. You'll add them to your slices only if you kind of trust them, right? So if I'm just an attacker that creates a tons of symbols, and you ask me, I ask you, please put my symbols in your quorums, you'll be like, no, I don't know you. Why would I do that?
So any two ISPs that have more than $1 million in annual revenue will have to connect. But that's
yeah.
So you're thinking that somehow these connections trust will happen externally to the system for social structures?
Yes, exactly. Yeah. Yeah, that's the hypothesis.
But so if I make a mistake and I have to trust someone who's not trustworthy, then I become shooting myself in the foot and back and I put money.
Yes, but you have some redundancy, right? If you choose your slices to be large enough, and just one member of it's faulty, it's like in the traditional quorum system, like in the example at the beginning, if one was faulty, it's fine, right?
more like a
And in fact, is a few slides.
So this is kind of a generalization of traditional systems, where we all share the same core, very same.
Yeah, so basically, this is a generalization in 3 steps that we just went through. We have the classic model where everybody has the same form. Then we have the asymmetric model of Giuliano and Beckman, where everybody has different quorums, but they just pick them up, define them however they want. So it's kind of hard to argue that they're going to overlap sufficiently. And now we have FBA, where because we make those assumptions about assumptions, we get this transitivity property that will make it more likely, according to this hypothesis, that the whole system will have overlapping quorums.
Wait, so this, hearing you would say that it's everybody trusts the single quorum, it's a validator.
Ethereum is the classic model, right? Because the quorums are defined up front by, at least 2/3 of the state. Okay, so covered this a lot now with the questions, but the first takeaway is that in FBA, we do create an asymmetric quorum system like Giuliano and Beckman defined it, but we're relying on this transitivity property. And so since we obtain in the end an asymmetric quorum system, we could think, well, we're just going to take algorithms that work in the asymmetric model, and they're also going to work here. We have an asymmetric quorum system. But the big difference, note, is that in the asymmetric model, you have your list of quorums, you define it, you know exactly who your quorums are. Here, your quorums depend on what others do in their slice configuration. So when you join the system, okay, you make assumptions, but your slices, but you have no clue what your quorums are going to be. In order to compute your own quorums, you have to ask others in the system, hey, what are your slices? So this implies that we have a new type of malicious behavior in the system. Now nodes can lie or forge their slices and change my quorums, even if I'm well behaved. So malicious nodes can actually shape the quorums of well-behaved nodes, which is like a fairly new thing that we haven't seen in this models. That makes sense? Yes?
It's like you would want to know the quorums of only those who you trust, right?
Yes.
And they would, like if they were malicious, then you already have a bad quorum. But the concern
No.
that like this sort of amplifies the number of bad people in the quorum, they point you to only other bad people.
Yeah, so what they can do is amplify the number of quorums so they can mount a DOS attack, I guess, in some way. Or what they could do also, and we're going to see that in the next slide, is make your quorums much smaller so that you have less chance of intersecting others. So let's see an example. Okay, let's revisit this example. So here we said there's a unique quorum, which is the whole set. So we would think that safety is guaranteed no matter what. But in fact, two failures can compromise quorum intersection. Anybody guess how? So the trick is that, so we're going to introduce two malicious nodes in there, and they're going to change their slices. And node 2 is going to be malicious, and it's going to say, well, actually, my slice is just N1. And 4, same thing, say I have a unique slice in 3. Now we get two disjoint quorums. So two failures now have completely broken the system. So we have a new effect to take into account. Makes sense? Yeah.
A big interest because you could not tolerate 2 out of 4 failures in the classroom of that one, right?
So, but at least we could have safety for any number of failures. Right? We would lose liveness. Let's say if 3 failed and we have just this quorum, we'd lose liveness, obviously, but we still have safety. We would expect that safety holds up to 4 failures. Accuracy at this point, but not just 2.
The same thing is they're not using.
Yeah, you can't even tell that they're malicious. So it's a very insidious attack. But it's not that bad because once you have some redundancy built into your slices, you can actually tolerate nodes playing those kind of tricks. So in this example again, let's assume node B and B prime are malicious. So what they can do is remove those 2 slices here basically by saying, well, our only slice is back to N and N prime. Okay, so they remove that. Now we lost the intersection here, but this is not a quorum anymore because we haven't satisfied this 3/4 requirement here. So we have to add those 2 slices to get a quorum. Now we recover our intersection. Make sense? So in general, basically the worst thing that malicious nodes can do is make quorums as small as possible, at least for the point of view of safety and liveness. Now, if you start considering DOS attacks, as you mentioned, it can also make you have thousands and thousands of quorums. But, so in this example, let's say we have quorum intersection here, but it relies on just one link here. So if this node becomes malicious and says my only slice, then you can just cut off this branch and we lost the quorum intersection. Make sense? Cool. And so this will allow us basically to do a worst case analysis of the system with quorums that are as small as possible and get rid of this phenomenon in analysis. Okay. Okay, so this kind of concludes the first part of the talk. We're 40 minutes. There's like 2 more parts. We probably won't get to the third one. But I'm really happy that there's questions. It's interesting. Thank you. So the next part of the talk, we'll try to figure out a little bit what kind of structures are going to arise in federated. So we'll start with noticing that those quorums, they're not arbitrary like in the asymmetric model. In fact, they enjoy a property that we call quorum sharing. What does this property say? It says that a quorum is a quorum for all its members. If you look at the definition, it's right here. It's pretty obvious. Quorum must satisfy the assumptions of its members, and the member must be the quorum, so it's a quorum for the members. So this means that we can look at the system as just a set of quorums. We don't need to keep track of which quorum is a quorum of which node. Because we know a quorum is a quorum for its member and only its members. Okay? And we also know from the definition that the union of 2 quorums is a quorum. And now if we squint a little bit and we remember our undergrad mathematics classes, we might start to think that this starts looking like a topology, general topology. So what's a topology? It's a set of points that will be the nodes in our case, and a set of open sets that will identify with quorums in our case. And then there's 3 axioms. The empty set is open, the full set is open. Arbitrary unions of opens are open, and the intersection of 2 opens is open. So this slight problem here, in particular with this one, right? Because the intersection of 2 quorums is usually not a quorum. We have a small problem with the empty set being a quorum also, but it's so what we're going to do, we're going to say, well, let's just get rid of this axiom. And let's call this a semitopology. Okay? And interestingly, it looks like, I don't know, nobody's ever really studied those objects. They look like they're going to have almost no structure at all because we removed one of the important axioms. But it turns out that's not the case. So let's try to push this a little bit farther. What happens now if we start applying, asking questions and using some familiar notions from topology to try to, in particular, let's consider this system here. The question is, what does it mean to be in agreement? So here it looks like we have kind of 2 communities that are disjoint. Some quorums intersect here, some quorums intersect here, but there's no intersection between 2 communities. But still, we would like to say something useful about such a system. Maybe we have a blockchain and it's a really open system. We want to be really inclusive, and we might have people who have very different views, don't trust each other in the system. In this case, maybe we want to, it's fine for them to fork as long as they continue on their own side. That might be a feature we want to have in this. If so, we cannot define consensus as global agreements. That will work. So how do we define agreement is the question. And to answer this, we're going to revisit a very familiar notion from topology, that of continuity. So remember from calculus 101, the definition of a continuous function. Right, so this function here is continuous at point p equals 2. If for every open interval around the image of 2, around 3.5, we can find another open interval inside the pre-image of our interval, here 1.5, 2.5. That's the definition of what it means for a function to be continuous in general topology. Does that make sense? Okay. So what if we apply this definition to our consensus semitopology set? So here's the setting. On the left here, we have our semitopology of nodes. We're going to do binary consensus. So on the right, this is the image space. We have the discrete semitopology of 0, 1. Discrete just means that every set is an open. So we have 3 opens, 0, 1, the whole set. And then our function is going to be D, which assigns to each node its decision value in an agreement problem. Okay. And so in this case, for example, node n has decided 0 and node n prime has decided 1. So what if we apply the definition of continuity here? Well, it means that for every open around the image of n, every open around 0, signal 0, we need to find an open in the pre-image of 0. So let's assume the pre-image of 0 is this set, new set here, 0. Is this continuous? So if I take the pre-image of 0, I need to find an open set in the pre-image. An open set in the pre-image. Yeah, but the intersection, we got rid of this axiom. So yeah, so the answer is no, this is not continuous because we don't have an open set inside the set that is 0. So instead, this, now this is a continuous function at least at point n. So if you translate the definition of continuity, it just says if n decides z, then there is a quorum of n that decides z also. And this seems to be like a good definition of agreement for this kind of system where we might have different communities. And in fact, if you think about traditional consensus algorithm, usually a node is going to decide something when it's convinced that a quorum is going to decide that same thing. So it kind of matches the algorithms. And so we can say that in fact, the definition of agreement is computing a continuous function. It's kind of cool. That makes sense. Okay, so 5 minutes left. So we can push this very far, and actually we can push it maybe way farther than we should have. we wrote this paper that's just available on archive for now, but it's almost 100 pages. And we're just examining what kind of structure emerged with semitopology. And to entice you, I just copied a bunch of diagrams that we wrote in the paper to illustrate all kinds of structures that arise in these topologies. We really discovered a zoo of different structures. Kind of fun to think about if you're into topology and abstract mathematics. And it turns out that they also carry some relevant insight for the problem of actual consensus in a distributed system where you built a quorum system. And now, if I still had half an hour to talk, I would go over some of those. But maybe let's just do one real quick. 5 minutes left. So we can easily see that the semitopology partitions itself into a collection of sets that we call topens. Topen is a transitive open set. What does it mean? T is a topen if, well, it's open, and it's transitive, meaning that if O intersects T and T intersects O prime, then O intersects O prime. In distributed system vocabulary, T has a core intersection. So this property tells us that if we look at the system, we're going to be able to identify disjoint area of the systems for which we will be able to solve consensus. Okay. And how do we prove this? It's actually really easy. So we show that if we take two topens T and T prime that intersects, then their union is a token. So this means that every time I have topens that intersect, I can keep growing the token. And in the end, I'm going to end up with a disjoint union of maximal topens system plus some points that are no topens. Okay. So proof is, well, for the first item, we need to show that T is open. This is just by the union axiom. And then we need to show that O and O prime intersect if we assume that O intersects T and O prime intersects T prime. How do we do this? Super easy. We start with two of our assumptions. From this, because T is transitive, we deduce that O intersects T prime. Then we bring in our other assumption, and that's here. Now we have O intersects T prime and T prime intersects T prime. Again, by transitivity of T prime, we get O intersects prime QED. So seeing things in this abstract semi-topological model can make some of the properties much. Okay, so now we can skip
We have 10 more minutes.
10 more minutes. More question?
So, like, if basically this property in the previous figure is like, yeah.
Well, this one, for example?
No, I guess like the previous one where you had,
Yeah.
this one. So this means like the definition of agreement that you showed also implies that everyone like this 2, 4, 5, 6, 7, 8, 9, 10, 11, 12 have to agree on the same value.
Maybe it's not clear that, that this one, for example, is a token. So maybe only, I don't know, it was 4 here are a token together. But if you start including that one, since there's no intersection between this one, between 7 and 11, it's not going to be a token. So it's not as clear cut.
Like from the definition of the agreement, like if you choose a node in Q10, for example, it has to have the same value as another node in Q10.
Yes.
And now you can choose the one
Well,
that
no.
is also in Q9.
No, because it might be in Q11. So you have the choice. Either it has the same value as Q11 or Q10. So I'm not saying that everybody terminates. Maybe only Q11 terminates and not Q10. So a node in the intersection is fine because it's 11 in agreement with it.
I see. Okay.
This one.
I see. There is a core that cannot be.
Yeah. Okay, so since we have a little bit more time currently, we can go into second property I'm going to talk about. So tokens also have useful closure properties. So you recall in topology, the closure of a set is a set of points such that every point, all the neighborhoods of every point intersects the original set. Point is in the closure of R, point P is in the closure of R if every open neighborhood of P intersects R. It's a really standard basic definition for general topology. And if we apply this to tokens, we can see that there's 2 useful properties that we're going to use next. So if O is an open that intersects a token, then the token is included in the closure of the open. That might seem a little bit difficult, but if you actually write things down, it's super easy to see that it holds because the token has quorum intersection. So if you intersect it, and all of your opens are going to also intersect it, and therefore it's in the closure. Second property, if we have a set whose closure intersects token, then the set itself intersects. So let's translate it to distributed computing by considering the reliable broadcast problem. Okay, so in reliable broadcast, we have a designated sender that wants to send a message to the whole system. And we want to guarantee that even if the sender is malicious, either everybody receives the message or nobody receives the message. It cannot be that I receive it, but Joachim doesn't. Okay. And so what's the protocol for this? So in a classical threshold, here, even non-malicious. Sorry. This is a threshold quorum system where we have 3F+1 nodes. Every quorum is 2F+1 nodes. And this is the BRCA broadcast protocol. Broadcast. So it just has 4 rules, pretty simple protocol. So if a node N notices that the sender announced B, then the node voids for the first rule. The second rule is that if you notice that 2F+1 nodes voted for V, then you accept V. third rule is that if you notice that f plus 1 node accepts v, then also accepts v. There's two ways you can accept value v. And finally, if you notice that if a full quorum accepts v, then you deliver it. And that's the end of it. Okay, so let's see how this works. Message diagram. So here we have one malicious node out of 4, and our malicious node is going to try to make N2 and N3 deliver the message, but not N4. Okay, so it starts, it announces value v only to N2 and N3. Okay, then according to rule 2, in the vote phase, N2 and N3 are going to vote and send their votes to everybody. And the adversary also votes, but sends its votes only to N2 and N3, so it's trying to isolate N4. Okay. So at this point, N2 and N3, they're going to see that the quorum voted the values according to rule 3, they're going to accept it. But N4 at N2, it only has received votes from N2 and N3. That's my quorum. There's one, it can't do anything. Okay, so now in the accept phase, as you said, N1, N2, N3. So N2 and N3 send accept. The adversary is also going to send accept N2 and N3 because he wants them to deliver. But N4 is still short of quorum. But you can now apply rule number 3. This is f plus 1. It receives f plus 1 messages, and so now it knows that N2, N3, and itself have accepted, and apply rule 4 and deliver. So the adversary was unsuccessful in trying to deliver. What does this have to do with closures and semitopologies? Well, you can note that this algorithm relies on 4 crucial properties of a simple system. The first one is that there are at least 2 f plus 1 well-behaved nodes. And this way we can make progress if the sender is correct. Okay. 2 set of 2 f plus 1 nodes have at least 1 well-behaved node in common, so we're never going to be using the agreement which value is %. And then there's 2 more important ones here. If somebody delivers, it means there was a quorum 2 f plus 1 that accepted. And out of these quorums, there will be f plus 1 well behaved and also accepted. And so this will trigger rule 3 on everyone. This is property 3. And then property 4, if rule 3 is triggered on someone, so f plus 1 accepted, then there is at least 1 correct that have accepted among those, so meaning the adversary cannot fool anybody into accepting using all of those. And so when we compare with semitopology, we realize that the set of f plus 1 nodes is a set that intersects every quorum. That should remind us of the closure we just discussed. In fact, property P3 and P4 are exactly the 2 properties that are listed above if we see the system as a semitopology. So this means that if we replace f plus 1 by some kind of thing in terms of closure, we can port this algorithm as is to semitopology. So in the classic quorum system with nodes, here we'll have a semitopology with a token T. We're going to replace threshold 2 f plus 1 by just quorum open, and we're going to replace threshold f plus 1 by the existence that R that blocks such that the node n is in the closure of R. Okay, we plug this into the algorithm, and that's it. We have reliable broadcast on semitopologies or FBA systems.
How do you verify the open property?
What do you mean by verify?
I mean, I have to guarantee that it works.
Yeah, so that's the internet hypothesis. The translation of the
verify, the first one, Ethereum stickers are on it.
Yeah.
This is a bit of a more of the open property.
it's actually the same. It's the translation in topological language of the three intersections. And the fun thing also is that even if it doesn't hold for the whole system, we proved before that your system partitions itself into a set of disjoint tokens. So we know that we will be able to do broadcast in each, and they won't like taint each other and screw things up. How am I doing on time? Maybe one more thing. Sure. Okay, so this relies on being able to actually compute whether a node is in the closure of something that has accepted. Right? So we said the definition of closure is that all your open neighborhoods intersect the set. Okay? So in distributed computing language, all your quorums intersect that particular set. But we don't know which are our quorums, right? We don't, as we said before, we don't get a list of our quorums like in the asymmetric model. Our quorums depend on the configuration of others, and we have to ask others about their slices and compute and so on. So what if there's a Byzantine node that just doesn't respond? I will never get the full list of all my quorums. So how am I going to compute whether I'm in closures? So an interesting observation here is that we can actually do this using a distributed algorithm. So here's an example of this figure. So let's say we have the following slices in this system. So this means that we are going to have three different quorums: this one, or this one. And let's say now we have a set of three nodes here who all accepted some statement and tag them as blue star. And this node wants to know whether it's in closure. So what we can do is have each node do the following. If the node notices that all its slices contain at least one node that has the star, then it's going to adopt the star also. So what this means here, well, this node has a single slice here with the stars. And to adopt a star, this one also, this one also. Okay. And now, recursively, these two are also going to notice that all their slices contain a star. So it doesn't have to be everybody in the slice, just one of those slices. Okay, so they adopt a star. And finally, our initial node adopts the star and knows it's in the closure of nodes that initially have the star. This is the algorithm formalized in semitopology, and we have a theorem that says when the algorithm terminates, you have exactly the closure of the set you started with. Okay. Final remark, maybe. After this, I wanted to show you how to actually solve consensus in such a system by starting with the Paxos algorithm and translating it. But I'm just going to say that solving consensus in the FBA compared to solving consensus in the traditional PFT quorum system model is a little bit more difficult because quorum certificates do not work. So in an algorithm like PBFT, maybe the leader notices that a whole quorum has voted unanimously for value, receives signatures attesting that, and then now you can tell everybody, hey, look, I have signatures attesting that there was a decision, everybody decided we're done. In this model, we can't do that because a quorum for me is maybe not a quorum for Joachim. So if I send you a set of signed messages, saying, hey, look, there's a decision, you might be like, well, this is not a quorum for me. I can't do anything. So we cannot use this quorum certificate trick, which means that it's actually very similar to solving consensus in the unauthenticated Byzantine model. So what we could do is, okay, we could use SCP, the Star Consensus Protocol that David devised, but we can also take another protocol that works in an authenticated model and run it in FBA, like information discovery hot stuff works. The only caveat is that we'd also need a leader election order. No time to talk about that. Okay, Paxos. All right, brings me to my conclusion. So in a nutshell, so the FBA model allows us to construct quorums in an open permissionless system that are highly likely to to intersect sufficiently by transitivity and without proof of stake. Quorums in the FBA model can be seen as a structure that looks like a topology, semitopology, and it's like a really rich structure and explainer powers. It's a really nice model, and I think it shows that the idea of FBA is actually a fundamental idea that shows up a lot of places in mathematics. And solving consensus in the FBA model is kind of reminiscent of solving it unauthenticated. Some open problems that remain. Yeah, we don't have a good way to do leader election in FBA. We have one that works in practice in SCP, but it's hard to say something very clear about it in theory. Can we use the trust information from the slide containing the slices to build Sybil resistant peer-to-peer overlays? Good avenue for research. And finally, how do we do cryptography in the FBA model? Like in some algorithms, like we can use, for example, aggregate signatures, threshold aggregation to speed things up. But here we don't have a fixed threshold; we have arbitrary sets. So can we figure out how to aggregate signatures in this type of scheme?
What's the problem? You can do aggregation across arbitrary access structures.
Maybe. Yeah, so different parties have different access structures. Okay, so if I aggregate for one party, it's not going to convince the other party. Can we find a way to aggregate so that I convince maybe a whole token? That would help a lot for this.
I mean, you realize hopefully by a bit mask tells you which
well, yeah, but if you do it for your quorums and you send that to me, my quorums are different. So
what I can do is like the largest thing that I'm seeing, I aggregate everything and I show you the bit mask and look for within that. And there's the best I can do because it's fun.
Yeah.
But in the bit mask, it's not like a list of all.
Well, there's one bit for it.
You don't know.
this is an open permissionless system. We don't even know who's in the system. So I have no idea how to do this. Just think it's an interesting question.
Is it a well-defined question? Or is it not?
No, it's not well defined. It's a hunch that there's something interesting there. So I'd like to avoid sending a lot of individual signatures around. So I'd like to have some kind of aggregation process, but that somehow.
Every node still has the aggregate signature.
But also what I would like to have is to have a way to aggregate, a way to prove to somebody that a certain threshold. Right? I don't want maybe to have to check every single identity. That makes sense?
Yeah.
I don't know. So I don't know. There's some work on multiverse signatures. Seem kind of related. I'm not a cryptographer at all. Okay, and finally, we have some references here on some of the papers in which the stuff I presented. And that's it.